acid chlorides. So this is the first of the carboxylic derivatives. So what is an acid chloride? So an acid chloride here is they synthesize from a carboxylic acid using SOCl2. Remember that it is a nucleophilic substitution reaction. The substitution reaction occurs because the OH here is not a good leaving group. So what we first do is, in place of chlorine directly, we use SOCl2 because it can help in removing the structure. So that creates acid chloride plus SO2 and HCl. So we can split this mechanism into two parts. So the first part is the conversion of OH into a good leaving group, and second part is to lose the leaving group, and finally the last part is proton transfer. So let's look at the first process. So let me write it down separately. So let's say we have a structure. So let's draw the reaction first. So let's say we have a carboxylic acid, OH, R. So we are saying a generic carboxylic acid, so I'm not taking any specific one. So the first reaction that happens is SOCl. So SOCl2 contains, this is the structure for SOCl2, which contains one lone pair of electrons. Now this SOCl2 gets attacked by the double bond. The double bond will attack sulfur, because notice that sulfur is an electron deficient molecule, so it contains a lot more than required. So now it attacks the structure. So when it attacks the structure, you end up with oxygen here, getting two lone pairs of electrons. So what's going to happen here is that this oxygen will donate one pair of electrons here and create a double bond. So this is the first part. Now when it attacks the sulfur here, attaches itself, you have oxygen, you have chlorine, you have chlorine. Now this oxygen here, when it attacks, it loses the electron pair, it gains the electron pair and becomes negatively charged. So this oxygen now gives an electron here, and the sulfur will release one of the chlorines out. So this is the first part that happens. So you lose minus Cl. So you lose the leaving group, and once you create the leaving group part, what will happen next is you have created the oxygen here, so the double bond, oxygen with a hydrogen and one lone pair and a positive charge. So remember that because this moves here, it creates a double bond, and oxygen, because it is losing a lone pair of electrons, it becomes positively charged. Now with this in mind, what will happen? So this Cl that is going here will attack the hydrogen. So when it attacks the hydrogen, this will donate its electrons back into the oxygen, resulting in a structure where you end up with double bonded oxygen on the top, so on the bottom, and oxygen with SCl O attached to the end structure with a double bond to the sulfur. Now this is the structure that you're left with. So here, because now we are bonding with oxygen here, so this creates a good leaving group. So this creates a good leaving group. So once it creates that good leaving group, now what will happen next is the second part will happen. So what will happen in the second part? Let us write it down separately. So in the second part we have, let me write it down as a clear path, the compound oxygen. So this is the compound that we talked about. So the chlorine nucleophile now has an easier chance of attacking the carbon. So this chlorine nucleophile will attack the carbonyl group. So nucleophilic attack. So when it attacks the carbonyl group, so now you end up with R single bond O, because it attacks the carbon, this one will go up. So the oxygen will get back 3 pairs of electrons and oxygen. So here you have chlorine, this structure now. So what will happen next is that the oxygen here donate its electrons back to the carbon, and this carbon will now donate its electrons back to the oxygen. So resulting in a structure where you would have R double bond O Cl plus S bond O minus double bond O and Cl. This is the structure. So what will happen again? This will go back here and create SO2 plus Cl minus. So because when it goes back here, the sulfur donates its electrons to chlorine and chlorine moves out, creating sulfur dioxide and chlorine. So notice that this is the product that we need. So this is the product that has to form. So again, the mechanism involves where we took first, we converted OH into a good leaving group, and second, we did nucleophilic attack. So we did nucleophilic attack. So this is the idea behind the reaction. Next, let's look at hydrolysis of acid chloride. So what happens in hydrolysis is addition of water. So when reacted with water, an acid chloride is generally an unstable compound, will react with water and form carboxylic acid. So it's basically the reverse of preparation that we talked about right now. So when you add water, an acid chloride becomes an acid back again, releasing HCl. So the mechanism involves nucleophilic attack by the water molecule, and you lose the Cl group because that's a good leaving group, and finally you undergo proton transfer where the hydrogen H2O molecule will lose one of the protons, finally ending up in creating the carboxylic acid. So this is the reaction that occurs. Next, since HCl here is the byproduct of hydrolysis, pyridine is the one that we use to neutralize this compound to make sure that it stays neutral and it does not become acidic. So you do not want the reaction to be acidic. So what we do here is we use the compound pyridine. So pyridine creates pyridinium chloride, which regulates the acidity of that reaction. So acid chlorides are also reacted with an alcohol. When you react with an alcohol, it creates an ester. So what happens here is the carbonyl group attaches itself in removing the proton. So the proton and the chlorine will create HCl, and the exact carbon will attach itself to the oxygen, resulting in an ester formation. So if you have a sterically hindered alcohols, will react more slowly. So primary alcohols can be acylated selectively in the presence of a secondary alcohol. So when you have one alcohol over the other, which one will be the one that the reaction will, where will the ester formation? So when you have two OH groups, where will the ester form? So this here is an alcohol that is tertiary. So this is a secondary alcohol, but here this alcohol is a primary alcohol. So the lesser the substituent, so the ester always forms at the less substituted alcohol group. So between the primary and secondary, the less substituted is the primary alcohol. That's why that carbon will be the one that forms the ester. So remember this principle here. Now, next one is the process of aminolysis of acid chlorides. So acid chlorides are generally used to synthesize amides. One way we do that is by adding ammonia. When you add two equivalents of ammonia, we get NH2. If you add a substituted ammonia, where we say a methylamines, that results in the methyl group formation. Remember that the reaction that occurs here is that when you take NH3 So one of the hydrogens and chlorine combines and the nitrogen will attach itself to the carbon. The same thing happens with R and H2 as well. So the reaction only occurs when you have at least one proton on the nitrogen. The reaction will not be occurred on tri-substituted amines. So you need at least a di-substituted amines. So this is the, if you have two R's, so one H and one chlorine will combine to form HCl, and this nitrogen will go and attach itself to that position, so creating the amino compounds. So this is the ammonolysis of acid chlorides. Next is the reduction of acid chloride. So what do we do in reduction here? We are basically converting acid chlorides into a primary alcohol. So acid chlorides can also be reduced using the same compound that we generally use, lithium aluminum hydride. So how does the reaction occur? The common reaction, again, first thing is a nucleophilic attack, and because there are two groups that are leaving, that are nucleophiles that are attacking, hydrogen is got a not a good nucleophile, so Cl will be the one that leaves, resulting in the formation of an aldehyde. The aldehyde further undergoes a nucleophilic attack by the aluminum hydride compound ion, and then results in the formation of a general hydrogen structure, and the oxygen then undergoes proton transfer, finally creating the alcohol. So this is the reaction here of reduction of alcohols. So let's say we have a simple acid chloride. So let's say this is the acid chloride that we are working out. So what happens when you have LiAlH4 is, remember that LiAlH4 splits into Li and AlH4 minus. So AlH4 minus can also be written as Al, hydrogens on each corner with a negative charge. So what happens now? The negative charge goes to the hydrogen. The hydrogen then attacks the proton. So this results in the formation of this structure. So the oxygen now, so the carbon will donate its electrons to the oxygen now, creating oxygen negative and a chlorine here and a hydrogen here. Now between the two compounds, now what will happen here is that the oxygen will donate its electrons back, and between the two groups that are attached, so chlorine is the good leaving group, so it will leave, resulting in the formation of an aldehyde. So resulting in the formation of an aldehyde. The aldehyde again gets attacked by aluminum hydride, and again what will happen again? The same thing again. The oxygen gains its 3 pairs of electrons, and there are 2 hydrogens that are attached. Now the oxygen that is present here, because it's in an acidic medium, this results in the formation of, you have H3O plus. So what will happen now? The oxygen now attacks the proton, resulting in the final formation of OH and 2 H's. So resulting in the formation of a primary alcohol. So this is the alcohol that forms. So we started with, so butyl hydride, so butyl chloride, but you're ending up with butanol. So this is the structure that we end up with. So the acid chloride becomes an alcohol, so in this reactions. Now how do we stop this reaction to form an aldehyde? Is we use a compound called lithium tritetrabutoxy aluminum hydride, where in place of hydrogen, for 3 of these positions we attach butoxy ions. So we call that terbutoxy ions, and leaving only 1 hydrogen. So when there is only 1 hydrogen left, there is no excess hydrogens to let the reaction continue to form an alcohol. So the reaction stops at aldehyde formation. So this reagent is more selective and reacts with acid chlorides faster than aldehydes. So the aldehyde becomes isolated. So this is one of the reasons why it can become isolated, because the reaction equilibrium is more driven to remove the product than remove the reactant than the product. So these are the reactions. The next one is an acid chloride reacting with a Grignard reagent. What happens when it reacts with a Grignard reagent is creates a tertiary alcohol. Remember that when it undergoes reduction, it creates primary alcohol. When you react it with a Grignard reagent, it becomes a tertiary alcohol. So what happens here is that in place of chlorine, you get two R groups that attach themselves to the carbonyl carbon and an OH group. Again, the same reaction as before. In place of H minus from before, we get R minus here. The R minus is the one that you end up getting from RMgBr, which results in formation of R minus and MgBr plus. So the R minus will attack the carbon. This becomes the nucleophile. And because R is not a good leaving group, the Cl will be the one that ends up leaving the structure. And first it creates a ketone. So remember this principle here. In reduction reaction, where we use LiAlH4, first you start with an acid chloride. So acid chloride under reduction creates aldehyde and then further creates a carboxylic acid, alcohol, primary alcohol. But when we do Grignard reduction, using RMgBr, so you have acid chloride first creates a ketone and then the ketone further becomes reduced to form a tertiary alcohol. This is the basic sense of the reactions what are going to happen. So if you remember this framework of the reaction, it makes it easier to understand the whole of the reaction. Next, let's take a look at reactions of acid chlorides. What are the common reactions? One of the reactions instead of Grignard reagent to be used is what we call the Gilman reagent. So Gilman reagent is lithium dialkyl cuprate, where we have lithium on one side and copper with two side chains attached to it. So we can use that instead of the Grignard reagent. When we use that instead of the Grignard reagent, it basically undergoes, so it only adds once to the acid chloride. So remember that before it stopped adding at the reaction, it does not stop at ketone. It further continues to create the tertiary alcohol. But if you want to stop it at the ketone structure, then we have to use Gilman reagent. So Grignard creates tertiary alcohols. But if you don't want to continue from ketone to tertiary alcohols, we use the Gilman reagent. So Gilman reagent is used to create ketones. So remember that lithium terbutoxy, aluminum hydroxide, that is used for creating aldehydes. Gilman reagent is used for creating ketones. So these are the summary of the reactions that we saw in this lecture. So when we use an alcohol, it creates an ester. When we use H2O, it creates carboxylic acid. When we use SOCl2, the carboxylic acid can be converted into an acid chloride. When we use Gilman reagent, it creates ketones. When we use Grignard reagent, it creates tertiary alcohols. When we use lithium terbutoxy, aluminum terbutoxy hydride, that creates aldehydes. When we use lithium aluminum hydride, you create primary alcohols. When we use excess amines, we create disubstituted amines. When we use primary substituted amines, you get carboxy diamides. So amines, depending on the type of amine that you use, you end up getting the final compound. And finally, when you add an alcohol, you get an ester. So this is the summary of the reaction. So because remember, this summary is good because it can help us in forming new compounds by the synthesis strategies. So it's a good important one to remember for the topic of synthesis strategies. So if you want to screenshot it, pause the video right here, or if you have your slide, just use the slide to remember what are the reactions that are generally useful here. So try this problem now. So they are asking you to fill in the necessary reagents for the reactions below. So first we started with a carboxylic acid and we are making it into the aluminum acid chloride. So when you convert from carboxylic acid to acid chloride, we have to use SOCl2. So this reacts with SOCl2. Next, this structure now results in the formation of a combination structure where we have to use this entire structure formation now. So we are basically, in place of removing chlorine, and we are adding this structure. So the structure that we are adding here is this entire structure. So which means that here we are basically eliminating the reaction to form a side chain. So that reaction can be achieved by using the pyridine. So the alcohol that we are using, so the structure that we are using here results in the formation of OR. So first we convert this original acid chloride and add it with this particular structure and end up creating the final structure. So the structure that we can use here is copper, the Gilman reagent, because remember that Gilman reagent only adds once, so it only adds once here to that entire structure. So we are using this reaction here. So remember that we are using this reaction right next to the double bond. So that creates this structure. So here we are using cyclopentyl group taken twice, CuLi, copper lithium. Now what to do when you want to create this into this structure here? So for that we are using pyridine and THF and this structure here, because this structure is the one that's getting attached to the double bond. Again, remember that it's still pyridine and we are adding an amine group here. So the amine here basically is R2NH. So the H and the chlorine will combine and form HCl, and the NR2 group, so this entire structure will attach itself onto the structure. So this is the reaction that we can use. So pause the video right here and try to solve these reactions one by one. Next, let's move on to the next one, acid anhydrides. So anhydrides are basically synthesized by heating carboxylic acids, especially excessive heating of carboxylic acids. What does it do is we are basically dehydrating carboxylic acids. So when you remove water from carboxylic acids, the one, for example, let's say if you have two acetic acid compounds, the OH group and the H group combine and form H2O, and this will vaporize. And whatever is left, the oxygen will now attach to the carbon and form acetic anhydrides. So anhydride removing water. So this reaction only works for acetic acid to make acetic anhydride. Most acids cannot survive extreme temperatures. Some acids do that at low temperatures as well. So a more practical synthesis requires using an acid chloride and reacting it with a carboxylate ion. So we use the acid chloride and we use a carboxylate ion and attach themselves to finally form NaCl. So this reaction generally takes place at basic conditions. So meaning that there is no proton transfer involved at the start. So the first thing that happens is the nucleophilic attack. So the carboxylate ion will attack the carbon, and the chlorine is the good leaving group. So that will leave, finally creating the anhydride, the final anhydride formation. So what are the reactions of acetic anhydride? So the NaOH here is used to deprotonate the carboxylic acid, and it's used to yield the carboxylate ion. So when we use alcohol, one of the common processes of creating esters is what we call that esterification, is the process of creating an ester. One of the processes is Fischer esterification, where we use a carboxylic acid and an alcohol using an acid catalyst under acidic medium. What will happen here when we use alcohols here? The H and the OH will finally create H2O. The methyl group will attach to the oxygen, creating the ester formation. Whatever is the alkyl group attached to the OH bond will bond with the oxygen, creating the ester. So this mechanism is the common consistent mechanism. So the first thing that happens here is proton transfer. The oxygen attaches itself to the hydrogen and creates the imbalanced structure, and the methyl alcohol will attack the carbon, resulting in the formation of this intermediate structure, and then the methyl alcohol undergoes proton transfer, creating the intermediate again. Again, another methyl alcohol will undergo proton transfer, leaving water will go out. The water, once it goes out, again another proton transfer will occur, finally creating the alcohol. Notice, remember the process: proton transfer, nucleophilic attack, proton transfer, loss of leaving group, and proton transfer. Remember that there are more proton transfers occurring in Fischer esterification. But the basic sense of the reaction is still the same: proton transfer, nucleophilic attack, proton transfer, loss of leaving group, and then proton transfer. This process with three proton transfers is exactly the same as before. Next, esters can also be prepared by treating an acid chloride with an alcohol. This we already discussed before. So when we use acid chloride and an alcohol using presence of pyridine, it creates esters. The reason we use pyridine is because HCl is formed and pyridine neutralizes HCl. Right? Pyridine neutralizes HCl. This is the reason why we use pyridine. So use that principle here and pause the video right here and try to solve these problems. Next, let's talk about the reactions of esters. So esters undergo what we call saponification. So saponification is the process of hydrolysis under basic conditions. When you can add NaO in presence of basic conditions, when you add water, it creates alcohol and carboxylic acid. So acid and alcohol are formed from ester. This process is called saponification, where we form acid and an alcohol in presence of using esters in basic medium. Now you can also hydrolyze esters under basic conditions as well. So the acidic conditions as well, that also creates the same acid and alcohol formation. This mechanism here, we call it the reverse of Fischer esterification. So this reaction here is called as the reverse of Fischer esterification. So you don't need to learn the mechanism, so just know the reaction and how it works. So the basic sense of the reaction is enough for here right now. So what happens here in this reaction is that the OMe here attaches to the hydrogen and this one attaches to an OH group so remember that H2O splits into H plus plus OH minus. So H plus will attach itself to OMe, OH minus will attach itself to the carbon, resulting in the formation of an acid and the alcohol. So this is the reaction. Next, esters can also undergo aminolysis to form amides. So how do esters do it again? Aminolysis here. So in NH3 now, so NH3, so you can form NH2 and H. So the OMe bonds with hydrogen. The NH2 will bond with the carbon, creating the amine group, amide and alcohol. So remember, ester creates amide and an alcohol when it undergoes aminolysis. So this process is really slow. That's why it's not synthetically utilized a lot. So the reaction will always favor the amide formation, but because the amides are more stable than esters, so they always favor the amide formation. So esters can also be reduced using reagents. When you use excess lithium aluminum hydride, esters can create alcohols. So what happens here is that OMe will combine with the hydrogen and the carbon combines with OH here. This combines with a hydrogen and this oxygen also combines with a hydrogen. So to finally create two alcohols that you have. So you need two equivalents of the reducing agent and there are two alcohols that are produced. So the mechanism is analogous to reduction of an acid halide with LiH. So if you remember from acid halide, we did the same reaction where we created an alcohol formation. But there the one another compound that you get was HCl, but here you get two alcohols here. Now, one of the other ones that we use instead of LiH is DIBA. So DIBA is isobutyl aluminum hydride. So instead of LAH, because LAH requires high temperatures, but a diba can be used low temperatures. And in place of creating two alcohols, it rather creates an aldehyde and an alcohol. So this ends up becoming H, and the hydrogen will attach to the carbon itself, creating an aldehyde and an alcohol. So remember that when we use LAH, you create two alcohols. So when you use diba, you create an aldehyde and an alcohol. So these are the reactions for esters. Next, when we use Grignard reagent, what will happen here is that esters also create the same as before any other compound, a tertiary alcohol. So they bond more and more and finally create a tertiary alcohol. So let's try this reaction here. So they're asking us to create the necessary reagents that are required. So the first thing we know here, it says that there is terbutyl alcohol, so tertiary alcohol. So remember that, and whenever you see tertiary alcohols, you have to remember that this is a Grignard reagent. So what is the Grignard reagent that we are using here is all of the groups that are attached are methyl groups. So which means that we are using CH3 MgBr, and we have to use, because how many are getting alcohol, so how many were taken here? We have 1, 2 and 3 and 4. So there are 4 of them, so we need 4 CH3 MgBr for this reaction. So, and it undergoes the reaction and finally creates all the OH groups. So all double bond O groups end up becoming OH. So there are 4 OH groups in total. So this part is what breaks up and forms terbutyl alcohol. Next, for this reaction here, notice that in this reaction we have only one alcohol formation that we do have here. So in the reaction that we have here, there is no alcohol addition, but basically we are adding hydrogens. We are removing oxygen and we are adding hydrogen, so which means this is LiAlH4. So LiAlH4 and ether, right? So that's the common reaction that we generally use. So here also we use ether because ether is the common solvent that we generally use. Why ether? Because notice why LiAlH4? Because notice that it's not terbutyl alcohols, it's just hydrogens that are added at each positions, and all oxygen groups here are also added with a hydrogen. So that's the reason why we use LiAlH4. If there was an aldehyde here, we would have said that this is diba, but notice that both are alcohols, which means that it's a lithium aluminum hydroxide. And note that all of them are primary alcohols. Because all of them are primary alcohols, now we can say that these are using LiAlH4. If you have tertiary alcohols here, all of these, the alcohols that you are forming in both these sites here are tertiary alcohols. That's why we can say that these are done using Grignard reagent. So this is the summary of that reaction here. So use the same principle now and try to solve these problems. So pause the video right here and try to solve these problems. Next, let's go to the last one, which is amides. Sorry, penultimate one, amides. Amides can be made by using any carboxylic acid derivatives, because remember the reaction, when we have NH3 from acid chlorides, we can create amines. When we use acetic anhydrides, NH3, again we can create amides. Again, when we use NH3 from esters, we can create amides. So these are the reactions that all the reactions from all the compounds can be produced. So with two equivalents of NH3, we can create NH2 amide formation here. So amines can also be hydrolyzed with H3O+. When you hydrolyze them, it creates carboxylic acid and ammonium ion. So ammonium ion and carboxylic acids. So the reaction here is very slow and it requires very high temperatures. So one workaround around that is the products here are always favored. So there is no reverse happening here, because the OH group here cannot act as a nucleophile and go back and form NH4+. So that's the reaction why it doesn't occur here. So amines can also be hydrolyzed under basic conditions when you add NaOH and in presence of H3O plus finally also creates the same reaction. The base catalyzed hydrolysis is even slower than acidic hydrolysis, so this will not occur as well. Amines can also be reduced when you use LAH. LAH, it basically creates from amide into an amine, so it makes it into an amine. So this mechanism is quite different from the others that we have seen, because this reaction here does not create an alcohol, it actually creates another amine. So amide, if you want to create from amide into amine, we have to use lithium aluminum hydride. So what is happening here is we are basically removing the entire carbonyl group while maintaining the nitrogen to be bound to the molecule. So this is the reaction that happens here. So use the principles that we just saw. So pause the video right here and try to solve these problems. Next, the last one is nitriles. So recall that primary and secondary alkyl halides are generally treated with a cyanide ion, which is the Cn minus, which can act as a nucleophile in an SN2 reaction. So alkyl bromides or alkyl halides, when we use sodium cyanide, it also undergoes substitution reaction, especially SN2 substitution reaction. So nitriles can also be made by dehydration of primary amide. So when you dehydrate by using SOCl2, that creates nitriles. So nitrile is a cyano group attached. So bond Cn is a nitrile. Now, so nitriles in general are hydrolyzed. When you hydrolyze them, first thing that happens is that a nitrile under hydrolysis first creates an amide. The amide under further hydrolysis creates carboxylic acid. So now it creates a carboxylic acid. Next, nitriles can also be hydrolyzed under basic conditions. Also, when we use basic conditions, it still creates carboxylic acid again. So when we use Grignard reagents, nitriles create ketones. So when we use Grignard reagents, the nitrogen is removed and the carbon attaches to the oxygen and two R groups are attached. So the R group form one of the Grignard reagents attach itself to the carbon, creating the Grignard reaction. Next, nitriles can also be converted into primary amines when we use reduction reaction. So when you reduce it with LAH, it creates primary amines. So this reaction is from a nitrile to an amine. So this is the structure when we use from nitrile to an amine. So use the principles that we just talked about. So pause the video right here and try to solve these problems. So with this, we end our lecture on carboxylic acids and their derivatives.